Okay, cool. So the recording is started. Right. Awesome. So, hi everyone. Today we have Yi Lin Lee from Indiana University Bloomington, and he'll be talking about an extension of Lindstrom-Gessel-Viennot theorem. Before we get into it, let's talk about our community guidelines, which are we're all learning. We are here to get to know stuff, talk about fun math. Everyone has something to contribute. If you're an undergrad or a faculty, feel free to share whatever thoughts you have. And finally, no one has all the answers, not even the speaker, even though they might. I completely trust you on that. And in case you want to help people in the chat who are asking questions, go ahead, feel free to do that. And Yelin, we will be monitoring the chat, so you don't have to worry about it. So in case there are
Sure.
questions,
Okay.
we'll tell you.
Mm-hmm.
Awesome. So Yelin, go ahead.
Okay, yeah. Thanks for giving me this chance to speak up here. And today I will talk about and introduce the Lindstrom-Gessel-Viennot theorem. So if you want to look at the slides, it's available on my website. And also you can see the paper on archive here. So today I will start from two motivating questions and then introduce what the Lindstrom-Gessel-Viennot theorem is. And then next, I will just move on to our new results and extension of Lindstrom-Gessel-Viennot theorem. And finally, I would like to talk about the applications and some open problems, especially on the tiling enumeration problem and the Jacobi-Trulli identity. Okay, so let's start with the first question. So let's consider a northeast-oriented square lattice. So we have this square lattice, and all the horizontal edges are oriented east. Vertical edges are oriented north. And we have some points, let's say U1, U2. These are the starting points of some paths, and V1, V2 are the ending points of the path. And we would like to know how many pairs of non-intersecting lattice paths from U to V do we have? And we two paths cannot start from the same point and cannot end at the same point. So for example, this is the one of the example that two paths, the pair of paths are non-intersecting. And we say two paths are non-intersecting if they do not pass through the same vertex. On the other hand, on the right picture, this is the case where two paths intersect. And if we have more passes, a family of paths, we say we say it's non-intersecting if any two of the passes are non-intersecting. So that's the first question. And the second question is that if we slightly if we slightly have two different ending points, let's say W1, W2 here, and we ask the same question: how many pairs of non-intersecting lattice paths from U to W do we have? So basically, the first question can be answered by the Lindstrom-Gessel-Viennot theorem that we will see later on. But for the second question, there's some issues. Okay.
I have a quick question.
Yep.
Do I always send U1 to W1 and U2 to W2, or does it not?
No, it's not necessary.
Okay.
Yeah, it's not. It could be arbitrary. We just need to let those paths non-intersect. So you could have like U1 goes to W2 like this, and U2 goes to W1 like this, and the paths are non-intersect.
Great, thanks.
Okay, so let me introduce the Lindstrom-Gessel-Viennot theorem. So in order to introduce it, I have to say something about the setting and notations. So first, let's consider a graph which is locally finite, means the vertex has finite degree. It's connected directly acyclic. Directed acyclic means that there's no directed cycle in the graph. And we can also assign a weight on each edge of the graph. Okay, and then if there's a path, the weight of path is defined to be the product the edge weight, where the edge is in a path. And if we have n tuples of paths, then the weight of this family is defined to be the product of each weighted path in a family. Okay, and now suppose we have two sets of distinct vertices of U and V, and we can think of U will be the set of starting points, and V will be the set of ending points of the path. And this notation means that it's a collection of a path going from UI to Vj. It's just a set of single paths. But now if we have n starting points and n ending points, so we have n paths connecting these two endpoints, and the way we connect those points naturally induce a permutation pi. This pi is called a connection type. So we say n tuple path has connection type pi, means that the path pi goes from UI to V pi of I. For example, if pi is an identity, then this just means that the way we connect those paths are the passes from U1 to V1, U2 to V2, U3 to V3, and so on. If pi is, for example, the transposition 1, 2, then this means that in this n-tuple path, the path U1 connects to V2, U2 connects to V1, V3 to U3 to V3, U4 to V4, and so on. Okay, and if we have the sub-zero here, it's just a subset. It consists of non-intersecting lattice paths of the connection type pi. And now we not only consider just enumerate the number of paths, we can consider its weighted sum. So here I use the GF, this symbol, to denote the weighted sum of the elements in that set. And the Lindstrom-Gessel-Viennot theorem works on the directed acyclic graph. And if there are two distinct set of vertices U and V, you just think of they are a set of starting points and set of ending points. Then it says that we have this identity. On the left-hand side here, we consider all the non-intersecting lattice paths going from U to V with connection type pi multiplied by the permutation sign, and we sum over all possible connection types. And it's given by a determinant of a matrix where the eigen entry of the matrix is given by the weighted sum of the paths going from UI to Vj. So this is the general version of the Lindstrom-Gessel-Viennot theorem. And there's a special case. So before saying this special case, let me introduce a notion, which is called a compatibility of these sets. So we say U and V are compatible if the only way to form the n-tuples of non-intersecting lattice paths is that the paths going from UI to Vi for all I. In other words, that is the case when the connection type is an identity element. So if we have this restriction where the set of starting ending points are compatible, then we have this simplified Lindstrom-Gessel-Viennot theorem. So the left-hand side here just reduced to a singleton. So remember, the original here is a summation of sine times the weighted sum. But here, in this case, if U and V are compatible, then this just reduces a singleton where pi is an identity element. So we have this term here, and the same right-hand side here is a determinant of a matrix. So this simplified version is actually the most commonly used version when people apply the Lindstrom-Gessel-Viennot theorem. Okay, so in other words, the general version of the Lindstrom-Gessel-Viennot theorem provides the signed enumeration of families of non-intersecting paths, but we also have the straight enumeration if two sets are compatible. Okay, and there are numerous applications of Lindstrom-Gessel-Viennot theorem. This include, for example, the enumeration of like semi-cylinder Young tableau, plane partitions, Lorentz or domino tilings, and it also provides a way to evaluate the something called Henkel determinants, or gives a combinatorial proof of some determinant formulas like Cauchy-Binet formula or Jacobi-Trudy identities. So there's a survey paper written by Crichton Saylor. Yeah, if you are interested in this part, I suggest you to look at this paper. Okay, so let's go back to our first question. We have starting point U1, U2 here, V1, V2 here. And you can observe that the way to form a non-intersecting path is that you can only go from U1 to V1, U2 to V2. It's impossible to have a non-intersecting path connecting U1 to V2 and then U2 to V1. So in this case, we say the sets U1, U2, V1, V2 are compatible. So we can apply the Lindstrom-Gessel-Viennot theorem. What we need to do is to compute the entries of the matrix N. So the 1, 1 entry will be given by the number of paths going from U1 to V1, which is a very elementary problem, which is 5 choose 2, which is 10. And 1, 2 entry is given by the number of paths going from U1 to V2 is 5 choose 1. And U2 to V1, you can do the similar things and get those 4 numbers. And you put it in the matrix and compute the determinant, which gives you the answer. That's the answer to the first question. Okay, so let's look at the second question.
These were
okay.
Sorry, can I ask you a question? These calculations were for just the only time we cared about non-intersecting paths was just to establish that they are compatible. And then from here, it looks like we're counting just all paths.
Most of the application that I saw from the literatures that they establish it where the path has compatible starting ending points. Yeah, that's most of the results that people applied, that people used.
But my question is the things we're counting, and these are just all paths from U1 to V1 and U. Oh.
Yes. Yeah.
Okay.
Because you can, in this case, you cannot have V1 to V2 and U2 to V1, and the paths are not intersect.
But the sort of converse of that is not true, right? There are some U1 to V1 and U2 to V2 pairs that intersect.
Oh, right.
So are we?
So we only care about this. Sorry, yeah.
I'm sorry. Are we counting those intersecting pairs of paths as well in this?
No. We only consider the non-intersecting paths, the number of non-intersecting. Yeah.
So this manages to rule out those intersecting pairs where U1 goes to V1 and U2 goes to V2.
Right. Yes.
Okay. Thank you.
Okay, so let's look at the second question. If we have W1, W2 at least 2 positions, then in this case, both combination types are possible. So you can have U1 to W1, U2 to W2, which is non-intersecting, and also have U1 to W2, U2 to W1, and the paths are non-intersecting as well. So in this case, U and W are not compatible. But of course, we can still apply the Lindstrom-Gessel-Viennot theorem. But in this case, on the left-hand side is actually the sum of 2 terms. The first term corresponds to the combination type identity. The second term corresponds to the combination type transposition 1, 2. But there's a problem because of this permutation sign here. This is -1. So actually, the result we have is the first term minus the second term is given by the determinant of the matrix. But this is not the thing we want. We want the straight enumeration. So in other words, we want the first term plus the second term. So how to find the total number of families of non-intersecting paths if those starting ending points are not compatible? Okay, so let's go to our new results. So let me first give you an overview of these new results. So our setting is that we work on the directed acyclic graph with one special property. I will explain this special property later. And then we have two sets of distinct vertices of G. They are not necessarily compatible. They could be at an arbitrary position on the graph. And the new result is the straight enumeration. On the left-hand side, it's just the weighted sum of all non-intersecting lattice paths with all possible connection types. And it's given by a determinant of a new matrix M star, where the ij entry of this new matrix is given by the sum of products, the sign of the path, and the weight of the path. And the path is these paths are the paths going from UI to BJ. And here, this is a new thing, the sign of the path. So the key idea is that we associate the path sign to each path on the graph. It's just plus or minus 1. And the upshot is that this path sign, in the expansion of the determinant M star, this cancel out the effect of the permutation size on the left-hand side of the Lindstrom-Gessel-Viennot theorem. So that's the key ideas. I'm not going to give you the proof here. It's quite technical and a long proof, but that's the whole idea behind it. So next, I will just introduce what these properties are and how to associate the sign to a path. So any questions so far? Like there's something in the chat, so let me see.
We do have a question in the chat. So Rob asks if the determinant of M star different from the determinant of the original path of the matrix M.
Yeah, they are totally different. Yeah, it's different matrix M star. Yeah.
Because, for example, like this will be assigned, like this matrix will have pluses and minus signs, right?
Yeah. So some entries might be negative, not positive. Yeah. We will look at an example later on. So I always say the matrix M star and the original matrix N are very different. Yeah. Okay, so let me start with this special property. That is the graph G has an upward planar drawing. So there's many ways to draw a graph on a plane. So this is a special kinds of ways we draw the graph. It's drawn in a way that each edge is a line segment that is either horizontal or up pointing. And because we require planarity, so two edges may intersect except at vertices of G. So no two edges may intersect except at the vertices of G. So here are our typical examples. The square lattice that we oriented like what we saw at the beginning, and the triangular lattice oriented in this way. But you may see that there's some edges pointing southeast, but if you rotate the whole graph like counterclockwise 60 degrees, then you will get it upward pointing edges. So here we require that our graph G has an upward planar drawing. But sometimes it's difficult to characterize what kinds of graph has this property. And let me give you another definition, is that we say the graph is an ST planar graph if it's a planar acyclic digraph with only one source and one sink. And these two spatial vertices lie on the outer face of the graph. And there's a theorem says that if the graph G has an upward planar drawing, if and only if this graph is a subgraph of an ST planar graph on the same vertex set. So maybe let's go back to see these two examples. So you can see that the bottom left, this vertex is the unique source. In the top right, this vertex is the unique sink, and these two vertices lie on the outer face of this whole graph. And similarly, the bottom left, this vertex is the unique source, and the bottom right, this is the unique sink. Okay, so now we just consider our directed acyclic graph having an upper planar drawing. You can think of it, it's a subgraph of an ST planar graph. Okay, and then next, want to know how to define the path sign. So we'll consider a graph, ST planar graph. So first, we have to define something called left side of the path. So instead of looking at it, let's just go to the example. So here, this is an ST planar graph. Each edge are pointing upwards. And we have the path here going from U to V. And we define the left path is a region bounded by the following edges. So these edges are the paths going from the leftmost path going from the source to U, together with the path itself, and the leftmost path going from B to this sink T, and together with the whole left boundary of the graph. So on the right picture, the left side of the path is the region bounded by those red edges. Okay, and then we let L of P be the collection of the starting and ending points, which are on the left side of the path, which includes U and V. For example, if A, B, C, D are the other starting and ending points of other paths, in this case, A, B, U, V are on the left side of the path P. So we say, well, the collection L of P contains A, B, U, V, while C and D are not. And the path sign is defined to be -1 to the power of size of L of P. So in our previous case, there are 4 elements in the set L of P, so the path sign is positive. Yeah. Okay, so let me just state the main results. So now we focus on the graph having an upper planar drawing. And in other words, you can think of it as a subgraph of an ST planar graph on the same vertex set. And we have 2 sets of distinct vertices, U and V. You can think of they are just the set of starting points and set of ending points. The matrix M star we saw before is defined to be the product sign times a path sign times weight of the path and some overall possible paths going from UI to VJ. And we get the straight enumeration of non-intersecting paths, which is given by the determinant of absolute value of the determinant of M star. Okay, so let's look at the second question. So because what we saw previously that the original Lindstrom-Gessel-Viennot theorem doesn't work in this case, that's because these U1, U2, W1, W2 are not compatible. But we still want to know how many non-intersecting lattice paths do we have in this problem. So we can apply our new results here. And we want to compute the entries of the matrix M star. Okay, so let's start with 1, 1 entry. So that is the path going from U1 to W1. So here you can just look at the left picture, U1 to W1. In this case, here those red edges form the left side of this path. And in this case, U1, U2, and W1 are on the left side. So there are 3 elements in the set LOP. And there are 4 choose one such kinds of paths. So if you just sum up, find the product of these 2 numbers and sum all of the possible paths, this gives you the 1, 1 entry will be -4. And similarly, if you look at the path going from U2 to W1, in this case, U2 and W1 are on the left side. So there are 2 elements in the set of LOP. And so this contribute the positive path sign. And the matrix 2, 1 entry is 4. Okay, let's look at another 2 entries. It's a little bit complicated. So for paths going from U1 to W2, there are 2 cases. The first case is that the path going from is illustrated in this green path. In this situation, that W1 is not on the left side of this path, and there's only one way to do that. Just you start from U1 going up to the end, and then going right. So there's only one such kind of path. And in this case, U1, U2, and W2 are on the left sides. So this contributes -1 in the 1, 2 entry. The second case is illustrated in this blue path. It's a situation that U1, W1, U2, W2 are on the left side. So the path signs is positive, and they are 6 choose 2 minus 1, such kinds of paths. So 1, 2 entry is -1 plus 14, which is 13. Oh, sorry. Okay. And you can do the similar analysis for the paths going from U2 to W2, and end up with -3. So if you put everything together into the matrix, compute the determinant, and you will get 40 in this case. Okay, so that's and how we use our new result to compute the second question. So I think it's good time to pose for questions. Okay, so let's just move on to the applications. So first, I would like to talk about the enumeration of tilings. So let me just briefly give you an overview of what the tiling enumeration problem is. So a tiling is a covering of a region on a plane using a given set of tiles without gaps or overlaps. So in particular, in this talk, we will focus on the region, which is called Arctic diamond. It's the union of all unit squares in the region bounded by this inequality. And this picture is the case when n equals 4. A domino is a 1 by 2 or 2 by 1 rectangle. So on the right side, this is an example that we use dominoes to cover the Arctic diamond region. We just call it a domino tiling. So in this field of combinatorics, we would like to know how many tilings do we have? Is there a nice formula? So in particular, the number of domino tilings of Arctic diamond is pretty beautiful. It's given by a power of 2. The result was given by Elkis, Larsen, Kruger, and Propp in 1992. And also we can consider the holes in the region. So for example, in this picture, there are 4 holes in the Arctic diamond region. And if there's a hole, then this unit square cannot be tiled by dominoes. And on the right side, this is an example if we have a domino tilings of the region with holes. And the question is that how does the number of tilings change if we have a slightly different position of holes? Like if we just slightly move the hole, maybe this hole 1 unit above, then the number of tilings is increased or decreased. Yeah, so this is a typical problem that people ask in this field of combinatorics. And there is an survey paper written by James Prop. If you're interested in this part, you can check his paper. Okay, how does the tiling problem related to Lindstrom-Gessel-Viennot theorem? So there are many ways to count the number of tilings. And there's one way that involves the Lindstrom-Gessel-Viennot theorem, which is called the path method. I'm not going to explain the details here, but you just need to know there is a bijection between all possible tilings and all possible families of non-intersecting lattice paths. So here, just a particular example that works for Aztec diamond. But this works, we have to choose the starting and ending points of paths suitably, so that if we want to make the Lindstrom-Gessel-Viennot theorem works here, those starting and ending points need to be compatible. So in this case, you can think of the path start from left, I mean southwest boundary of the Aztec diamond region, and ends at the southeast boundary, and the path going from left to right. And this is actually called a de-nanoing path. Okay, and similarly, if there's a hole in the middle, then we can still construct a bijection between tilings and non-intersecting lattice paths. But in general, if there's a hole in the middle, then the starting and ending points are not compatible. Okay, so let me talk about one natural generalization of Aztec diamond, which is called Aztec rectangle. Because in the previous picture, for the Aztec diamond region, 4 sides have the same length. For Aztec rectangle, we just need to have unequal lengths. And here we also colored those unit squares in a checkerboard coloring fashion. On the right picture, here is something we call mixed Aztec rectangle. It's obtained from Aztec rectangle by removing some black unit squares. I mean, by removing all the black unit squares on the southwest boundary. I mean, it's 5. And then remove all the white unit squares on the southeast side. So we just obtain this mixed Aztec rectangle. Yeah, so one result about it is that if we have arbitrary unit holes in the mixed Aztec rectangle region, and we can translate these unit holes. We translate the unit holes, it's called a color preserving translation, means that we translate the holes along the same direction with same distance at the same time. And the color preserving means that the underlying checkerboard coloring is preserved under this translation. And the result is that these domino tilings, the number of tilings is invariant under this color preserving translation. So for example, on the left picture, and on the right picture, they just translate those holes to the right by 2 units. And I claim that, well, if you count the number of dominant tilings on the left picture and right picture, they are equal. Is there a question?
Ewan, what do you mean by provided all units are still contained in the region?
But when we translate those holes, the holes might be moved somehow. Will be moved to the outside of the region.
All of them the same amount.
Yeah.
Okay.
I mean, if we have 6 unit holes here, and after translation, we also want to have 6 unit holes in the region. Yeah.
Okay. Okay. Cool.
And the idea of it is that, so we use lab bijection. We just turn these tiling problems into the lattice path enumeration problem. And because of these holes, the set of starting and ending points are not compatible. So we can use our new results to write down a matrix M star for both cases and argue that the determinant gives the same number. Yeah, so that's the basic idea.
Do all the units holes need to be all like translate all together, like when you move them?
Yeah, translate all together.
Oh, okay.
Along the same direction or within the same distance. Yeah. Okay, so let's move on to next topic about Jacobi-Trudy identity within the last 15 minutes. So before stating the Jacobi-Trudy identity, I need to give some definitions. So let's start with a partition of an integer. It's given by a lambda. I can write it as k tuples lambda 1 to lambda k in a way that those numbers are weakly decreasing and they all sum up to n. And there's a natural representation of the partition lambda. It's called a Young diagram. So at the first row, just put lambda 1 unique squares. At the second row, you put lambda 2 unique squares, and so on, and so that those those unit squares are arranged in left justified rows. So this is an example for partition 431. Okay, and the semi-standard Young tableau is a filling of the Young diagram with positive integers, and such that if you just put some positive integer in it, the numbers are weakly increasing along rows and strictly increasing along columns. So this is an example. Okay, now we let x, the variables x1 to xn, x1, x2, and so on. These are the countably finite, countably infinite set of commuting variables. And the weight of each semi-standard Young tableau is defined to be x1 to the t1, x2 to the t2, where ti's is the number of times I appears in this semi-standard Young tableau. So for example, here 1 appears twice, so this corresponds to x1 squared. 3 appears once, so this corresponds to x3. So in this particular example, we have the weight x1 squared, x2, x3, x4 squared, x5, x6. Okay, and then, now finally, we have the definition of sure functions. There are many ways to define it, but one way we can write it down is given by the weighted sum of all semi-standard Young tableau of shape lambda. Okay, and then there's two more. The complete homogeneous symmetric functions and elementary symmetric functions are defined like this. It's a sum of a monomial, but for the complete homogeneous symmetric functions, we allow repeated indices of x. And then for the elementary symmetric functions, those indices must be distinct. Okay, and then Jacobi-Trudy identity says that given a partition lambda, then we can express the sure function as lambda to be the determinant of a matrix, where the entries of that matrix is just a homogeneous symmetric functions. And there's a dual version. If we take the conjugate of the partition lambda, then it's given. It will be the determinant of a matrix, and the entries is given by the elementary symmetric functions. So today we just focus on the first one, the first version of the Jacobi-Trudy identity. The proof of it, the idea is that we try to interpret the sure function as lambda and the homogeneous symmetric functions Hn as families of non-intersecting lattice paths. Okay, so again, we will work on the northeast oriented square lattice lattice, and then we add a vertex at infinity. Let's say its coordinate is I comma infinity. And the only way to reach this point is by taking an infinite number of north steps along the line x equals I. So let's just look at this picture. We have some starting points at the bottom, U1, U2, U3, and some ending points, V1, V2, V3 at infinity. And we can only reach these points by taking the infinite many north steps, just going up along where this point is, along the line where this point is. Okay, and then suppose we have a path going from, let's say, U1 to B1. Let's assume the bottom line is the line y equals 1. So the y coordinates is 1. And we labeled each east step by the y coordinates where that step is. So these two horizontal step will be labeled by 1, will be by 2 here, 3 here, 4 here, 5 here, 6 here. And the weight is, again, is very similar to the weight of semi-standard Young tableau. So for this rate pass, the weight will be given by x1 squared times x3 times x5. And for the blue pass, the weight is given by x2 times x4 squared, and so on. Okay, so in order to prove the Jacobi-Trulli identity, we have to specify where the set of starting points U and V are. So given a partition, the set of points U and V are given here. You can check that the homogeneous symmetry functions is exactly the weighted sum of paths going from Ui to Bj. So I'm not going to explain the detail here, but yeah, you can check it. And if those paths are non-intersecting, then there's a bijection between those non-intersecting paths and the set of semi-standard Young tableaus of shape lambda. So let's go back to see this picture. There are 3 passes and they are non-intersecting. So the bijection is pretty straightforward. You see those labels, for example, for the rate pass 1135. So you just put those 4 numbers at the first row in the Young diagram. And 244 here, just put it in the second row in the Young diagram, and 6 here at the third row. And this gives you the corresponding semi-standard Young tableau. So actually, this is exactly this semi-standard Young tableau. 1135 at the first row, 244 at the second row, and 6 at the third row. Okay, so yeah, so there's a bijection between them. And the good thing is that the set of U and V, the starting and ending points, are compatible in this case. So the Lindstrom-Gessel-Viennot theorem works. How does this work? So let's start from the sure function S lambda. By definition, is given by the sum of the weighted sum of semi-standard Young tableau of shape lambda. Because of this bijection, you can think of it as the weighted sum of non-intersecting lattice paths going from U to B. And then because U and V are compatible, we can apply the Lindstrom-Gessel-Viennot theorem. And it's given by the determinant of a matrix where the Aj entry is the weighted sum of paths going from Ui to Bj. And this is nothing but the homogeneous symmetry functions. Okay, so that's the combinatorial proof of Jacobi-Trulli identity using Lindstrom-Gessel-Viennot theorem. Of course, the dual identity can be proved by the similar idea, but you just need to use different labelings. So we are not talking about this here. Okay, so that's the basic idea. And the key point is that the starting and ending points that we choose are compatible. Because of this, we can use the Lindstrom-Gessel-Viennot theorem to prove Jacobi-Trulli identity. So at last, this open problem says that if we choose different starting and ending points so that they are not necessarily compatible, and the question is, can we find an analog expression of homogeneous symmetry functions, semi-standard Young tableaus, and even establish an analog version of Jacobi-Trulli identity? Yeah, so that's an open problem for everyone. If you are interested in this problem, you are welcome to discuss with me. Yeah, so I think that's the end of my talk. Yeah, thanks everyone. Oh, by the way, there's some references here. So if you are interested, you can take a look at those papers. Yeah, thank you.
Awesome. That was such a wonderful talk. Let's thank the speaker. Cool. Okay, the floor is open for questions.
Yes, there's
Andrew, if you
something in the
wanna
chart. So
go ahead. Yes. So one of the questions is that Robbie asked about the determinant M star matrix. And so he was asking about if it's related to the permanent of the matrix M.
well, let me see. Permanent. It's a totally different matrix. I mean, the permanent M and determinant of M star are very different. They are not equal.
I guess to clarify, I'm asking whether the determinant of M star is equal to the permanent of M. So you take two different matrices and evaluate the two different functions. Do you get the same thing?
No, I don't think they are equal.
Okay.
They are not equal. Yeah.
Okay, thank you.
Andrew, do you want to ask your question? So Andrew is asking, can we generalize? Oh, okay. Can we generalize upward planar directed acyclic graphs by considering these drawn without edge crossings on a cylinder, with the sources living on the boundary of one end cap and the sinks living on the boundary of the other end cap? And if so, would your outputs?
Let me read this question. Without edge crossing on a cylinder. Yeah, I think my answer would be I don't know. It's worth trying to do this and see whether it works. Yeah.
Okay. Other questions?
I have a question. So you demonstrated with the Aztec rectangle with holes that, if you shift the holes in a certain way, you have the same number of tilings. Have you tried to come up with an explicit bijection for any of this? Have you considered an explicit bijection?
Okay, I think that's a good question. Yeah, I thought about this a little bit. I think the most easy way for me is to turn this into lattice path. Yeah, so maybe there's a simple bijection between tilings with holes holes translating with the holes at different positions, but I think it's not very direct. Yeah, they could have a bijection, but at this point, I didn't see how it works. Yeah.
Wow. I just realized for the example you put on the screen, I believe we have a bijection between the empty set and the empty set, because I don't think there are any tilings of these.
Yeah, that's true. Yeah.
Okay, so that's still open up explicit bijection for the whole shifted.
Right.
I just wanted to ask one. For the final open problem question, have you played around with it? Do you have any idea what it could be? Is it even a shoe function on the left side?
Okay. I think I did a little. I did some small examples like for n equals 2.
Yeah.
And even work on the square lattice, and I the thing we get is even not symmetric, I think. But maybe there's a hope that we can express it as maybe a combination, linear combination of some symmetric functions. I'm not sure, but that could be one direction. Yeah.
Interesting. Yeah, that's a fun question. Cool. Are there any other questions? If not, thanks to speak again. So wonderful talk. And I am going to stop recording now. Thanks.